Good afternoon, everybody. So I'm just waiting, I guess, for folks to say hello on the chat. Give me an opportunity to know that there are folks that are watching. I will mention here, as it's the start, basically it's 1 o'clock, that there is a little bit of a delay. There's some latency, about 10-15 seconds or something like that between what you're going to see on the screen and when I actually say it. So please do, have just a little bit of patience. I guess we'll have some patience with one another here as we make our way through this. Hi, how's it going? How's it going, Blake? Hi, Michael. So that's me saying hello. You probably get a little bit of an idea about the amount of delay. So when y'all have questions, just note that it's going to take me 10 or 15 seconds to actually see them and start responding to them. So a little bit of patience hopefully is in order here, and we'll see how it goes. Hopefully it goes well. I do want to mention here that, hey Josiah, I will mention also that once the stream is concluded, I will be posting it into the links, into content, and the link will actually go in the announcement for the stream as well. So you'll be able to find, if you need to, you'll be able to find the link to this YouTube video of all of the interactions that we've had. So hopefully it'll be useful to you. I did do a stream this morning for one of my other courses, and what I found out, what I learned is that while the interaction isn't quite as back and forth, it's not so instantaneous, means it's probably a good idea for me to have a little bit of something to talk about and things like that. So, and then as questions arise, just type them into the chat. I'll get to all of them. I'm going to do a quick check to see if we had any questions out of the discussion boards. I didn't see any. I checked a little bit ago, so let me look right now and see what if anyone posted questions for the live stream. So it looks like no one posted any questions for the live stream for today yet. So I'll just assume that the questions are going to come from you all that are currently watching. So I'll start off by saying I do think it's probably will. And like I said, just go ahead and start asking questions now if you want them answered. I'll talk a little bit about an overview of what I think is going to go on for the rest of the week here, and then I'll answer your questions as we go along, and I'll pause to make sure that there's an opportunity for you to ask follow-ups and things like that. So hopefully this will work out okay. So I am planning to have an exam after we complete our review this week, as I've mentioned in my the announcements that I've been making, and we're going to do it online, and you'll have a couple of days that you can decide when to do it. But there will be a time limit on it, as we've talked about, or I've mentioned in the announcements. So what I'd like to do now is I'm going to use my very sophisticated paint program over here to do some drawing for equations and solutions and things like that if we want to talk about them. So just to let you know about what the exam is going to be over. Remember what we talked about before spring break. We've been dealing with Chapter 4 and Chapter 5. Chapter 4 and Chapter 5 is Chapter 4 is on forces and Newton's laws. And Chapter 5 is going to be on circular motion and then Newton's law of gravity. So those are the two chapters that you should be focusing on. Hopefully you've had a chance to look at the extra homework that I've posted for you to complete this week, so that you'll have a chance to do those before the test, so you get some practice in it. So Blake has a question here, and I saw it go by earlier, so this is a little bit more delayed than it normally would be. But Blake has a question of how often we're going to be having these streams, and I've My plan is to have them about once a week. If you want to have them more often, that is a possibility too. Once I get used to using the software and stuff like that, it'll probably become a little bit easier for me. So if you request them, no problem. And if you'd rather meet not face to face, but if you'd rather meet individually, then we can do that maybe via Zoom or something like that, so that we get an immediate question and answer going on between us. But for these where I want to post them, I think it's probably best, post them and share them with everyone. Then I think it's probably best that we do these live streams, simply because recording a Zoom meeting is extremely resource intensive, and it would take me a really long time to actually, it would take hours for the stream of that, or the video of that, to probably be rendered and stuff like that. So this will be available practically instantaneously. So that's the nice thing about this. So that's one reason why the delay that you're experiencing right now in asking your question and me answering it might be worth it for the future, for the fact that we can post this really quick and have it ready for you. So is that okay, Blake? Is that good? Lauren is asking on the test, how much of it is going to be multiple choice versus free response. I expect I'm going to be doing pretty much the same type of test, the same sort of distribution as you did for exam 1. So about, what was it, about 60% multiple choice, about 40% free response or calculational style questions. So I'm going to try to keep that the same, even if I sort of reduce the amount of questions maybe. Well, I'll see about that. I still have to think about how I want to do that. But I think it's going to be the same distribution, Lauren. Okay. Okay. Like says that's good. Okay, cool. So I'm going to start a little bit of review here, just so that we have something to sort of talk about. Feel free to ask any other questions that you want as we stream here. So, and just as they occur to you, they don't have to be about what's going on the screen right now or anything like that. So, if you have questions about format or anything like that, ask them there. Ask them as they come to you. And if you have questions about, I'd like to see a little bit of, get a little bit of help on an example problem or a homework problem or something like that, just ask it as they come to you, and I'll get to it as soon as I can. So, so let's talk a little bit about where we were at the end last time, before spring break, and see what we've talked about since the first unit was completed. So, and I'll use the scratch pad over here to sort of do that. So, chapter 4, and this is going to be my awesome handwriting as determined by mouse. So we did chapter 4. That was on forces and Newton's laws specifically. Okay. I know, pretty good handwriting. All right. So, what you should be thinking about out of chapter 4 is Newton's laws are sort of your guidepost here. So we had 3 Newton's laws. We had Newton's first law, which said that if the net force acting on an object is 0, there's no net force acting on an object, it'll move with constant velocity. Newton's second law was really important. It said that if an object does experience a net force, then the acceleration that it experiences is the net force over the mass of the object that's receiving the forces. And Newton's third law characterized how interactions between pairs of objects happen. That if one object pushes on a second object, then the second object pushes back on the first with the same amount of force but in the opposite direction. So it really those 3 rules sort of describe the overall way that forces, what forces do to objects, and how forces are really interactions between pairs of objects. You can't, something can't get pushed without pushing back, because there's a symmetry to that. So remember how that works. And then chapter 5, just as an overview, was, oops, well, here we go. Now we've got some I'm going to use the eraser because I had skills like that. All right, here we go. Okay, so so chapter 5 is circular motion. And in addition to circular motion, we talked about gravity. And a little bit of astronomy in there as background to tell us about how gravity works. So those are the two main topics that we dealt with out of chapter 5. Circular motion was basically, the idea was that when an object is moving a circular path, it has to continually change its direction of motion. That counts as an acceleration even if the object's speed stays the same, the direction of its velocity is continually changing. That's an acceleration, and we figured out that the acceleration when an object is moving in a circle had two important parts to it that were key to understanding how circular motion works. First of all, the direction of that acceleration, the direction that the velocity of the object must change, is always towards the center of the circular path. So it continually gets deflected towards the center of the circle as it moves. So we always know what the direction of the acceleration that an object is experiencing when it's moving in a circle. It's towards the center of the circle. The magnitude of the acceleration is always equal to the square of the speed, v squared, divided by the radius of the circle the object is traveling in. So you know both the magnitude and the direction of the object's acceleration if it's moving in a circular path at constant speed. And then you can just apply Newton's laws, Newton's second law to that. You can say, well, the net force acting on the object has to be equal to the mass of the object that's moving in the circle times that amount of the centripetal acceleration, that acceleration that we calculated, v squared over r. And the direction of that has to be towards the center of the circle all the time. So it really is just Newton's second law all over again from chapter 4, but with the special situation that we know how to calculate directly what the acceleration needs to be and which way it is. Then gravity was this idea that all objects experience an attraction toward one another that is proportional to their mass and inversely proportional to the square of how far apart they are. And gravity then can give rise to circular motion in the form of orbits and stuff like that around the Earth, around the Sun, whatever you choose. So I think that overall gives you a picture of what we've been looking at in this unit. Hopefully it reminds you a little bit about what's going on. Are there any questions now? I'll pause for questions here for about 20 seconds or so to see if you've got something you want to know about that. If there's a particular style of problem that you want to hear about, or there was something in the new homework that I assigned that is perplexing. So go ahead and give me a little bit of feedback on this. How's it going? What questions do you have that I can answer for you? And I'm going to clear this out just so that we have some space to write when I need it. So if you want to respond with no questions, if you don't have any questions, then that lets me know that you're just want me to go on with maybe, I don't know, doing an example problem or something like that from homework. I can do that too. Okay, so Josiah asked if I could work out the first problem from the latest lecture notes, and then Avery asked if I could do the second one. So, and okay, I've got a bunch of good questions. So Josiah's was in first, so we'll do that one. Could I work out the first problem from the latest lecture notes? So, let's have a look at these notes here. So, this is the one where it says your friend is riding on a sled. To help get them moving, you push on her shoulders downward and to the right. The rightward component of your push is 255 newtons, and the downward component of the force of your push is 180 newtons. Your friend and the sled together have a mass of 83 kilograms, and they accelerate along a flat horizontal surface at a rate of 2.85 meters per second squared. The questions, there's a number of questions that go along. It says, what's the normal force acting on the sled due to the snowy surface, and what's the frictional force acting on the sled? So, I'll draw then sort of what the situation looks like. So here's the sled. All right, we got a sled, and then your friend is riding on your sled. This is Dr. K patented artwork there. So there they are. They're sitting on the sled, and then so there they are sitting on the sled, 2 legs, and then what we've got then is a situation where we got to draw the forces that act on them. So it says that there's a force of your push. So you're pushing on her shoulders. Okay? And notice how there is a vertical component of that, and there is a horizontal component of that. And it says in the, I'm going to write down P sub x here. And then here's P sub y. Okay, oh, sorry, I've got that mixed up. Totally mixed up. This one is P sub y. There's the vertical component. Sorry about that. Okay. So this one is P sub y, the vertical component here, and then there's an x component down there, which is horizontal. And we know what those strengths are because the problem says what those strengths are. Okay? And then the sled and the person have weight, so I'm going to put that down there so I don't make the drawing more messy. So there's the weight of the person. That's the gravitational force acting on the person and the sled together. The ground is pushing upward on them. Okay, so I'll just draw that. I'm going to draw a little bigger. So there's what we call the normal force. And then as they're sliding to the right here, there's a frictional force that opposes the motion. So there's the frictional force. So those are the 4 forces that act on the person. This is your push, which has horizontal and vertical components to it. There's their weight. There's the gravity. The earth pulls them straight down. The surface of the ground pushes up, and the frictional force resists the motion. And what we know, a couple of other things that we know about this, I have to go back to look at the other things I know. So one is that this person's mass is, along with the sled, is 83 kilograms. And then I also know that this person is, it's not a force, but I'm going to put it up here anyway. I mean, I should maybe use a different color. We'll see if I can use a different color. This will be awesome. Okay. There we go. Look at that. We got red and everything. Okay. This person and the sled is accelerating in the direction of your push. And it's, let's see, 2.85. Gets a little messy. 2.85 meters per second squared. We move it in like that. All right. So there's their acceleration is that. And let's see what else we know. Oh, we also know we know the strength of Px and Py. So I'll just put those there. Px, we happen to know, has a strength of, so this is the rightward component of your push, is 255 newtons. So that's a given. 255 newtons of force. And the vertical component of your push, you're pushing downward a little bit as well, is 180 newtons. So this summarizes all the information that we're given in the problem. And then the question is, what's F? Don't know that, so we'd like to know what that is. And then what's N? So that'd be another thing we want to know. What is the normal force, the strength of the normal force? Okay, so that's what we're being asked. All right, so now let's find those things out. So I worked this out a little bit in the lecture notes as well, but I'll sort of repeat it here so that you can sort of see what the situation is here. So what I will do is let's go after the frictional force first. So what this means, since we are seeing here that the frictional force is a horizontal force, it's always parallel to the surface. In this case, it's the ground that's exerting the force. So the ground is exerting this, and that frictional force is parallel to that. So it's a horizontal force, which means that when I look at and start my analysis, I'm going to say, well, I want to know what is the net force in the x direction. Because we're going to use that. Because that's going to involve the frictional force, and that's going to allow us to solve for it. Okay, so then we start asking ourselves the questions. Remember the three questions that we had about all of the forces that are listed here. Okay, so the force of your push, does it have a horizontal component? It sure looks like it. There is one. Now, is it all horizontal, or is just part of it? Well, just part of it in this case. And is it plus or minus? And we're going to say to the right is positive. So I'm going to put in, I say the amount of the horizontal component of the force is p sub x, which we'll put in the strength in just a little bit, but we're going to have the symbols here first. And it's in the positive direction. Okay, continue around. The weight, does that have a horizontal component? Does it have an x component? Now it looks purely vertical to me. It's always straight down. Same thing for the normal force. So neither one of those contribute anything. Then if I look at this one, well, the frictional force, that has a horizontal component. It's all horizontal, so it's the whole thing. So we don't have to pick out just a piece of it. It's the whole thing is horizontal. And then the direction is in the negative direction because it's to the left, and we say to the right is usually our positive direction for horizontal. Okay, so there's the net force. Now, according to Newton's second law, the net force should be equal to the mass of the object. And we have the net force right here. It should be equal to the mass of the object times whatever acceleration it's experiencing in the direction that we're talking about. So I'm just going to, it's not really skipping a step, but I just want to skip a line here. The net force in the horizontal direction should be equal to the mass of the object. In this case, that number that we would put in there is our 83 kilograms, times the acceleration that they are experiencing in the x direction, which you'll notice the acceleration we have here is purely in the x direction, and it is positive. It's the magnitude of the acceleration is 2.85 meters per second squared, and it is going to be to the right, so we're going to put a positive number there. Okay, so now let's put in our numbers. We're solving for f here. What we see is on the left-hand side of this equation that we just built is 255 newtons minus f. We're going to leave f as a symbol because we do not know it. So we're going to leave it as a symbol, and we're going to solve for it. And then the mass that we put on the right-hand side here is our 83 kilograms. That's the mass of the thing that's doing the moving. Times the acceleration we're experiencing. We're going to kind of run out of space here, but we'll make do. 2.85. And it's meters per second squared. I'll just express that there, I guess. That goes in there. Oh, I guess I ran out a little bit of space. Okay, so now what I have is I can solve for f. We could do a little bit of algebraic stuff here. I'm going to plug it into my calculator. I even brought it along. Look at that. It's home now. Okay, so it's going to be 255 minus 83 times 2.85. And I get, the number I get is 100. When I solve for f using algebra, I get 184.5 newtons. And how I get that is, to solve for f, I add f to both sides to get this on that, and bring that over to this side. And then this number right here, 83 times 2.85, I'm going to subtract that from both sides using algebra. So the final frictional force ends up being 255 minus whatever number this is. So I'm going to pause and let Josiah or anyone else ask any questions on that. I will get to the other questions here, Avery and Lauren's questions, once I'm done with this problem. But I want to make sure that this is clear first. Okay, so go ahead. If you don't have any questions on this, just say no questions on that or something like that. Or just at least, one or two people say that so I know that it's okay to move on. Okay, so Josiah says no questions on that thing. So that's clear? All right. Okay, cool. So this is what I'm going to do. I'm going to clear this now, because it looks like folks have had a chance to ask questions on that part of it. I'm going to clear this bottom part, and we're going to go to the second part of the problem, which asks, what is the normal force that acts on the person that's exerted by the earth upward on them to support them? Okay, so we see that the normal force is a vertical force. So to analyze that one, we're going to have to look at the net force in the y direction. Okay, so again, now we're going to go around the horn, all of our questions, or all of our forces, and ask ourselves the three questions of those as well. So we'll start with the push. The push does indeed have a vertical component. It's P sub y. There is a component which is downward. So it's not the whole push, but part of it. The part of it is P sub y. Now normally upward we take to be positive, so I'm going to say the magnitude of that force is our 180 newtons. That's how hard you're pushing downward on her shoulders. And since it's downward, I'm going to put an explicit minus sign there to indicate that. So that's the first force. We dealt with the push. Now we go to the weight. Okay, the weight does have a vertical component. It is vertical. It's also downward. And it's all downward. There's no right or left to the weight. It's all straight down. Okay, so that's that one. And then I go to the normal force. I ask myself the question again, does this have a vertical component? You bet. It's all vertical. And then this one is plus because it is upward. Okay, and then I ask myself the question about the last force, the frictional force. Does that have a vertical component? Nope, it's purely horizontal, we can see here. So we can skip the frictional force. It doesn't contribute to the up and down net force. Okay, so there we go. And according to Newton's second law, this net force needs to be equal to the mass of the object, in this case it's the mass of the person and the sled together, times their acceleration in the vertical direction, because we were looking at the net force in the vertical direction. Now here comes the key. Is the sled accelerating up or down? No, it's moving purely horizontally. It's accelerating horizontally, but it is not accelerating up or down. So that means it's the acceleration in the vertical direction is 0, which means this whole term is 0, because no matter what their mass is, of 83 kilograms in this case, multiply it times 0 and I get 0. The net vertical force has to be 0. And this allows us then to solve for n by simply adding py and w to both sides to cancel them on this side. And that means that the normal force here will be equal to, to isolate n, first I add w to both sides. 0 plus w gives positive w. Then I still have negative p sub y over here. I'm going to add p sub y to both sides to get rid of that one as well. So plus p sub y. There we go. All right, now we've got them all. Now, here's the little side note thing. The weight, if you want to calculate the weight of something, I'll put it right here. The weight of, I guess I could just put it right here. The magnitude of the gravitational force acting on this person at the surface of the Earth is their mass times the acceleration due to gravity. Okay, so that tells me what the mass of what the weight of the person and the sled together is. The mass is 83, which means their weight is, I'm going to use that m times 9.8. I'll use 9.8, I guess. So I do 83 times 9.8. I put it in my calculator. I get 813.4 newtons. So I'll just write that down here as a reminder of the force that I'm going to put right there. I'm going to move that right there. P sub y, we already were given that in the problem as 180 newtons. So now I can plug in all the numbers that I have just figured out. I've got 813.4 newtons plus 180 newtons. And when I add those two numbers together, that will be what my normal force is. And I plug it into my calculator, so you get 993.4. Okay, and that solves that problem. So the outcomes of this, what I want you to take away from this is, first thing you should do is you should draw a free body diagram that uses the information that you're given in the problem. The free body diagram is draw the object whose motion you care about, then draw the forces on the object as good as you can. You know, the force of the push had both horizontal and vertical components, so I drew it as an angle down. I knew some of them were purely horizontal, like the friction. I knew some of them were purely vertical, but I drew them and I labeled them. Then I looked at and I said, well, I'm being asked about these other forces. Let's use Newton's second law to solve for them. Asking myself the questions about each one and then solving for it as necessary. Okay. Any questions on this one? I'll pause a second there to make sure that Josiah's question is fully answered here before I move on to a second question. A second example, I guess. Okay, Josiah says all good. Okay, so Avery then asks, can you go over the second example problem in the PowerPoint for 3:30? Let's see, I think that one was, I'm going to erase this now. I'm going to clear it so that we got a little bit of space. And the second one was, let me look at what that is. That's the car with a mass of 1,700 kilograms is going around a corner with a radius of 20 meters. The maximum amount of frictional force on the car's tires is 24,500 newtons. And the question is, what should be the speed limit for this corner? Okay, so the way to think about that one is we've got a car here, and let's say it. So I suppose I could try to draw it, but I'll do my best here. So I'm going to draw it as, oops, come on now. Come on, be good. There we go. All right. So this is going to be the car. You're looking at the car. It's coming right at you. This is my sort of patented car picture that we've done before. There are the headlights. And here's the grill. All right, here we go. And that's not a very good grill, but you get the idea. And I have some tires there. Under there we go, and then we got to have the windshield, of course, because otherwise you can't see. Okay, so there's sort of the car, and it's coming at you. And let's say it's going to make a corner. Okay, it's trying to make a corner. Let's say that it's trying to make a corner that, from our point of view, is to the right. If you're in the car driving at us, it's like you're making a left turn. Okay, so in other words, it's kind of, I'm going to think of this in 3D as this is like a circle that's in the plane of the car that we're sort of seeing at it here. It's trying to make kind of a corner like this. Okay, so it's kind of try to follow that path kind of out of the screen and along at us here. Okay, so that means that this car at this point right here, we know that the center of the circle that the car is traveling in is over here along this dashed line. From our point of view as we're looking at it, that is to the right. Okay, that's where the center of the car's circular path is going to be as it comes out of the screen at us and makes that corner. Okay, and I know that the car, I have to bring this up again, I know that the car has, and I'm going to put it down over here, the mass of the car is 1,700 kilograms. Okay, it's got a pretty hefty mass. Okay, so there it is. The radius of the corner. So let's say the corner's right, the center of the corner is right there. Let's say that this big black dot is the center of the circular path that it's traveling. That'd be a really tight corner, but we're not drawing everything to scale here. That distance from the car, oops, there we go, it's 20 meters. That is the radius of the car's path. That's going to be a 2 right there. Okay, maybe I can make it a little bit better. There we go. That made it look a little bit more like a 2. Okay, so it's 20 meters away. And I also know then that the center of the circle is right there, which is directly to the right from our point of view of where the car is. Okay, now here's the deal. I know that the direction of the acceleration of the car needs to be towards the center of the circle. So as we view it right here, we know that the acceleration has to be to the right from our point of view as we look at it. Now, if you're in the car, facing us, facing the other way from the way that we're facing the screen, if you were facing out of the screen at us here, then they would say, well, it's to the left of me. Okay, that's fine either way. It's just it's from a different point of view. So now let's draw the forces that act on the car. Okay, so one force is going to be the weight on the car. So gravity pulls down on the car. Okay, so there's the gravitational force. The earth is pulling down on the car. And then also on the tires, the road surface is pushing up on the tires. So that'd be the normal force acting on the tires. And then I drew one of the normal, actually it'd be on both of the tires, but I'm just going to say, let's say it's all, I'm just showing it on one tire. And the same thing is going to be true for friction. There's friction acting on this, and the grip of the tires is going to push them that directly to the left, or the right from our point of view. So this is the frictional force right here acting on the tires. So there's a normal force up, there's a frictional force to the right, there's a force of weight down. And those are the three forces that we can see that act on the car. Friction, the normal force, and the weight. Okay, so now I look at this and I say, all right, well, I'm being asked about, well, what's the speed of this? What is the speed that the car can have and still make the corner? All right, so this is how I'm going to analyze it. We're going to analyze it the same way we analyze any problem that involves forces. We are going to use Newton's second law based on what we have here. Namely that the net force that we care about, the net force is equal to the mass times the acceleration. Okay, now, here's the thing. We're using the circular motion type stuff now. What we're looking at here is we're looking at a situation where the car is accelerating. It's going to have to accelerate towards the center of the circle, which in this case is to the right. That gives us a hint that we should be looking at the x component of the net force and not worrying about the y components. The car is not accelerating up, nor is it accelerating down, and we're not asked about the normal force of the weight. We're asked about the speed, which is something that we use to calculate the horizontal acceleration towards the center of the circle. So in this case, that is going to be equal, according to Newton's second law, I'm just writing down Newton's second law at this stage, the mass times the acceleration in the x direction. But I know in this case, this is a little side note, so I'll put it over here. So this is part of our work. The horizontal acceleration, a sub x, is an acceleration that has to do with the object traveling in a horizontal circular path. Well, I know what the magnitude of that acceleration needs to be. We talked about it earlier in our little review. It's equal to the square of the speed over the radius. And in this case, that acceleration has to be, from our point of view at least, to the right, because that's where the center of the circle is. So what I'm going to say is, this is going to be a sub x. When we get to plugging in for a sub x here, I'm going to be able to calculate how much that is. Or this is going to be what the expression is for how we would calculate it. All right, now V is unknown, but we do know R. Not terrible, but okay. Now, here's the thing. Let's now analyze the left-hand side of this. What is the net force that acts on the car? That's just the horizontal. And I look around here and I see the three forces I have. The weight doesn't have a horizontal component, so we would skip it. The normal force doesn't have a horizontal component. Purely vertical again. We would skip that one. The only one that contributes to the net force is the frictional force. It's all horizontal, and it points to the right, so that's why I get a plus there. And that's it. The left-hand side is all of it is just plus F. Okay. Now, according to Newton's second law, that would be equal to the mass of the car times the acceleration it experiences. I know that that acceleration has a magnitude of v squared over r, and has a direction that I'm going to put in is positive. It is also to the right. So I'm just putting that in just to be explicit there, that it must be to the right. Okay. Now, the thing is, what we have been told in our problem is that the biggest amount of friction that you could ever get between the roadway and the tires of this car is 24,500 newtons. So I know that 24,500 newtons is the biggest frictional force I can have. Okay, so that's I put that in there on the left-hand side. The mass, I'm putting in numbers now. The mass of the car that we're talking about here is 1,700 kilograms. Now, I don't know the speed. That's actually what we're trying to solve for. So I'm going to leave that as a variable, but I know the radius of the turn is 20 meters. So I'll put that in there too. Now, what I'm going to do is I'm going to solve for the speed that the car can have and have 24,500 newtons be enough frictional force to make it go around the circle. It could, if it tries to go faster than that, if it has this much mass and that's the tightness of the circle, the faster it goes, the bigger the frictional force it would need. But if this is the maximum frictional force it can have, then this is the biggest speed it can have. So we're solving for what that biggest speed could be for which 24,500 newtons would be enough friction to make it go around. So I'm going to solve for V. This is just a little bit of algebra. What we would do is we would multiply both sides by 20, then divide both sides by 1,700. That would isolate V squared, so it would be just V squared on that side then. Then I'd have to take the square root of both sides to get that. So that's what the algebra would be. So let's do that. I'm going to take 24,500, divide by 1,700, and then multiply times 20. That number, then I take the square root of that number, and I see 16.98 meters per second. That is the number we would get. And that's how fast you can go. That's the maximum speed you could have and still do this corner. What I say in my solution in the lecture notes is that once I have that number, it's about 17 meters per second, a little bit under 17 meters per second. That's actually, if you did the unit conversion to miles per hour, that's about 38 miles per hour. The thing is, that would be a weird speed limit to see on the side. You can't go faster than 38 because everything is increments of 5. So that's why I would say if you were actually going to post the sign here because you're part of the Department of Transportation and you're trying to do your job here, you'd say, well, I'd put 35 miles an hour because that's under it. You can't say, well, let's make it 40 because 40 would be bigger than the 17 meters per second, and therefore they couldn't make the corner. So you set it at 35. Okay. Hopefully that's clear. Are there any questions on that one? That was Avery's question, I believe. anyone can ask questions on that to make sure that it's clear to folks. So I'll pause here and let folks ask questions. Okay. So Avery said that looks good. All right. All right, and then Lauren had, so I'm going to clear this one. Okay, thanks, Josiah. Let's see. So I'll clear this one. Hopefully that was useful to folks. And then, great, thanks. Awesome. All right, so Lauren's question then from before was, can you explain how weight, the gravitational force on Earth, differs as distance increases? Like problem 7 on the review homework, or a problem similar to it. Okay, sure, let me have a look at that one. Let's see. Was it question 7 or exercise 7? I'll assume. I'll look and see which one it looks like here. I want to make sure that I'm answering the right questions here. Maybe you mean the 7th question. Yeah, that's probably not. I don't have the questions in front of me what I asked. So. I'll just explain how the gravitational force on Earth differs as distance increases. So let's say that we've got a situation here where you're on here's the Earth. My circles are way better in person, I'm sure. But anyway, so if you're standing on the Earth here, on the surface of the Earth, then the distance between you and between the center of you and the center of the Earth then would be equal to the radius of the Earth. So I'm going to call that R sub capital E. So there's the radius of the Earth. That's how far you are away. Now if you want to calculate your weight using Newton's law of gravity, you'd say, okay, the gravitational force between two objects is equal to capital G times M1 times M2, gravitati and the gravitator, divided by the square of the separation between the centers of the two objects. So when you're sitting on the surface of the Earth, standing on the surface of the Earth, the distance between the center of you and the center of the Earth is basically the radius of the Earth. If you're really, really tall, it might be a little bit bigger than that, but the radius of the Earth is so big compared to the size of a human being that it's basically you're always the radius of the Earth away. So that's what's down here that's the square of the distance between the centers of the two objects. So your weight on Earth's surface is equal to the universal gravitation constant, that's that 6.67 times 10 to the minus 11th number. Then you'd take that, you would multiply times your mass, then you'd multiply times the mass of the Earth, and then you would divide by the square of this distance, which would be the radius of the Earth if you're standing on the surface of the Earth. Now if you're over here, let's say you're way up here. Okay, so you're way further away. You're up in like orbit or something, like super high Earth orbit. So now the distance between you and the surface, oops, I'm not going a very straight line, but imagine it's straight. That's way higher now. That distance is way bigger than before. So instead of it being, just this far, now it's this far. Let's say that this distance between here and you, or here and your new position up here is, say it's 3 times further. So instead of it being just one Earth radius, it's 1, 2, 3 Earth radii up there. Well, now since you're 3 times further away, you still have the same mass, the Earth still has the same mass, and it's still the same capital G, but now you're 3 times further away. Because you're 3 times further away and it goes down by a factor of the square of that extra distance, it'd actually only be 1/9 as much gravitational force on you. If you were 4 times further away, it'd be a 16th. You see how it goes like the inverse, it's a fraction of the square. So if you're double as far away, if you're twice as far away, so if you're like here instead, well now you're twice as far away if you're here compared to if you were here from the center of the Earth. So you'd see 1/4 as much gravitational force. Here, since you're triple the distance away, you'd be 1/9. If it was even further, if you went way up here and you're at 4 times further away, you'd be 1/16 as much gravitational force. Does that answer the question? I'll pause and see what y'all say. Right. So Lauren asked, well, how do you know what the radius of the Earth is? Yeah, that would be something you would either have to look up. It is in the textbook. You can look at it in the inside front cover of the book. You don't have a inside front cover, I guess, because you have an ebook. But it is in the book. But it's also Googleable if you're just out and about. Just Google what the radius of the Earth is. Just make sure that you're using it in. If you want to use the units that we use here, make sure you're using it in meters, because a lot of times they'll give it in miles or kilometers. So you can just, when you Google it, you can just say radius of the Earth in meters, and it'll just give it to you. If it's on an exam or something like that, I'll give it to you. It'll be on the test. So you won't have to memorize it or know what that is. And for your information, if you want to know what it is, the radius of the Earth is equal to 6.37 times 10 to the 6th. And that's in meters. All right. So hopefully that was useful. Are there any other questions that I can answer? I'm going to clear this out in sort of preparation for the next. Let's see. Alexander's asking. I'm trying to see who missed your mark was. Alexander's asking, will the exam be in lockdown? No, I'm not gonna make you use a lockdown browser or anything like that. In fact, I think I've mentioned this before. I intend it's easy to miss because I know there's a ton of information out there. I intend when the exam goes out, during the time you're taking the exam, it's open book, open notes, open internet. So everything is going to be in play. You can use whatever resources you want, but I do expect it to be your own work. So, and since it's timed, you're not going to be able to get answers to questions in real time unless you have somebody sitting next to you. So please don't do that. Please do your own work. But it is open book, open note, open internet. So the questions that I'm going to put together are going to be ones that kind of like our normal questions. It's not really so much like questioning you on facts or things like that or definitions, which would be easily Googleable. It's stuff where you got to kind of know how it works and and know what the definitions mean in order to ask them. So no, I won't be doing a lockdown browser or anything like that. You won't have to worry about that. The same thing with the calculational problems. When you're, do your work as best you can, but they're going to be typed out, kind of like what you do with homework. So don't just give the answer. You have to write out your work. You don't necessarily have to put equations down there, but at least write down what you mean, and how you are arriving at the solution. And that's why I'm going to give you a little bit of extra time on these things too, because I don't want you to have to worry about, well, I'm fighting the browser or the equation editor or something like that. You don't have to use the equation editor if you don't want. But I'm trying to give you enough time so that you can think about it, come up with an answer on a sheet of paper or something like that, and then type in what you have. So that's why I'm giving you a bunch of extra time. And I'm considering shortening the test a little bit so that the exams aren't too long for you. So there are some other questions? And for your info now, I do have the homework quiz, that review homework 18, available. I can look at those questions now. I just found them. Okay, thanks, Avery. Avery says no questions. Just saw that. Let's see. Lauren's asking, question 6 on the review homework asks us to calculate the centripetal acceleration. Is that the same as problem 2 that we did from the lecture? Question 6. Let me look at question 6. It is similar to that. It's somewhat similar to that, yep. It's asking what's the centripetal acceleration of the car, so that would be something where we calculate it. And then it asks what the magnitude of the horizontal component of the normal force that would be required to produce that centripetal acceleration if there's no friction. So, yeah, I think that should, yeah, it's very similar to that example problem, except it's a banked corner now, but hopefully that's relatively clear how you would approach that. Right. Yeah, thanks for typing that out too, Lauren. I see that now too. So right, you should be able to do it in a very, very similar way. Let's see, Alexander asks, once the stay-at-home order ends, will we be allowed back in to do lab, or are we sticking with these online as well? The stay-at-home order it's independent of what the state colleges and universities are doing. So I'm planning for now to do online lab instruction. So I've done the activities. I've got the videos ready. I haven't finished editing them and uploading them yet, but I'll do that as we get closer to it. So it won't be until next week until we would have to do any labs, but they are going to be online. I would plan, this is my thoughts on what's going to happen. I think that the stay-at-home order is likely to be extended, and even if it is rescinded by the governor, I expect that the colleges and universities in Minnesota State are going to say, we're doing online instruction until the rest of the semester. That is what I'm guessing is going to happen. So I would count on this is the environment we're going to be in until the end of the semester. So I would not count on coming back to campus. That said, campus is open to you to do with as you will. It's just we don't want to have students gathering. So campus is open. I was on campus the day before yesterday, or no, it was yesterday. Some of the entrances are open, so you can go on campus to use the computer lab and things like that. But we are not going to be holding class, as far as I know, until the semester is over. So if you're planning on taking a summer class, it is possible that the stay-at-home order and the campuses will be open for summer session, but I wouldn't count on it. So it might be online instruction here through at least summer session 1. That would be my guess is where things are going, but I don't pretend to know it. So I hope that answers your question, Alexander. I don't think we're going to be doing any labs. I've already prepared to do the rest of the labs for the semester, which we're only going to do 3 more labs. The rest of the labs of the semester are going to be by, remote. And they'll be done individually. Any other questions that I can answer? You're welcome. Anything else? And all of these things are going to be, I'll just want to allay, I know, this is not, of course, this isn't the ideal way to be learning, I don't think. I mean, maybe this is good for some folks, but I think face-to-face instruction is my preferred method to go, and likely yours as well. But we're going to have to be a little bit relaxed, and it includes me. So when we get to grading homeworks and building exams and grading all these sorts of things, we're sort of just trying to get you through this, learning as much as we can, but I recognize that this is not what you all signed up for. It's not what I signed up for either, but we're all going to do our best. We're going to pitch in and try to get you through. And that's the whole point of what we're doing here. That said, if we do need to do more live streams like this, as I get better at it, and feel a little bit more comfortable with it and stuff like that, we may be able to do this a little bit more often. So let me know in the discussion boards whether you think it would be useful to have live streams maybe a little bit more often. And that's okay too. We can make that work. I'll say this: it's a lot of there's a ton of changes I need to make to my lecture notes, to like doing example problems and stuff like that. It's super complicated to build up all those equations with all the example problems worked out. It's way easier for me to do it in front of you here and explain it as we go, rather than try to guess what you might have questions on as we go through it. So if we want to do more live streams, that's a possibility. Just let me know what you think about it. That would save me effort on the other side, like trying to rebuild my lecture notes so that it's more understandable just by you reading it. But I do want to keep it so that there's flexibility, because the real possibility, grim as it may sound, is that there may be a number of us that are getting sick, and if we do, then I want you to have the flexibility to be able to do this, after you feel better in a week or two or something like that. And that's something I gotta be prepared for. Okay, any other questions here? I want to make sure that's everything's clear about that. And if you have more physics questions, obviously too, I'll just pause and wait. If you say no questions, then I'll assume no more. But you're welcome, Lauren. Glad it was helpful. Thanks, Blake. Okay, so you're feeling like you're kind of ready to go. At least you can get through the homework and stuff. Okay. So I'll wait just a couple more, just in case there's something else that you have questions. But so I'll wait about another 30 seconds or so and see how it looks. But otherwise, I'll wrap up. Okay. All right. Well, I guess I'm going to end it there then. If you do have further questions that you think of after the fact here, feel free to put them in the discussion boards. It's super. That's a really good way to get folks that get your questions answered and out there. But the other thing is, it lets other students who may have the same question, so I don't have to. They'll see the answers to that one too, and that saves me some time too, rather than answer a whole bunch of questions that end up being the same. So please use the discussion boards; they're super valuable for that. Thank you for your time and attention. Thanks for sticking with this. I know this is not necessarily what you signed up for, but we're all going to do our best and make sure you come out of here learning some physics and maybe have a little bit of fun with it as much as we can, at least. So we'll see you next week. I'll keep an eye on the discussion boards and let you know how that all works as well. So see you later. Have a great one. Thanks again for your attention.